In this section, we're going to learn about the derivatives of the polynomials and the exponential functions. So derivatives of a constant function. Suppose the function f of x is a constant function, then deriving a constant function, the answer will always be 0. Example, suppose we derive a constant function, say 5, the answer is 0. Or derive a constant function, say negative 100, the answer is still 0. So deriving a constant function, the answer is always 0. Next, derivative of a power function. Suppose we have a power function x to the n. Derive a power function, we have nx to the n minus 1. So let me write an example for this. Deriving a power function, say x to the 3. Your answer will be 3x to the 3 minus 1, which is 2. So whatever is the exponent that goes to the front, and then you reduce the exponent in the problem by 1. So it's 3x squared. Similarly, suppose we want to do derivative of x to the 100, it becomes 100 x to the reduce 100 by 1, so it's 99. So these are the derivatives of exponential functions x to the n, power function. Then you have derivative of a constant multiple. Suppose you have a constant and then a multiple f of x. The constant can always be moved outside. Constant times the multiple, constant goes outside, so you see a constant here and then you derive the function. Example, suppose we want to derive 5x squared. 5 is a constant, you can move it outside, so you have 5 and the derivative of x squared. And just now we learned the power rule of differentiation. So derivative of x squared, the answer is 2x, and simplify, you get 10x. Next is the sum rule. In the sum rule, you derive the sum of the two function f plus g. So all you do is you can distribute this derivative to each of the term, derivative of f plus derivative of g. Then you have difference rule, which is similar to the sum rule. Derivative of difference of two terms, you can distribute the derivative to each term. Then you have derivative of natural exponential function. Derivative of exponential is always the same. It's e to the x. So let's do some examples. Differentiate the following function. The very first function, the derivative is a constant. So you want to write derivative ddx of the function f of x. Derivative, the function is negative 10.2, which is a constant, so replace it. And the very first formula, derivative of any constant, the answer is 0, so we're going to write it as 0. Next, you have a 6th degree polynomial. So let me write derivative of the function f of x. The function f of x in the problem is a polynomial, so I'm going to replace it. Derivative of 1/2 x to the 6, negative 3x to the 4, positive x. So you're good to distribute this derivative to each of these terms. So the problem looks like this. Derivative of 1/2 x to the 6, negative derivative of 3x to the 4, and then positive derivative of x. Now derivative of a constant times a multiple, the constant can always be moved outside. So it moves outside. Then you have derivative of x to the 6. Let's do the power rule for x to the 6, and you have 6x to the 5. Similarly, the constant moves outside, you have 3. Derivative of x to the 4 using the power rule is 4 times x to the 3. Derivative of a function x, you can do the power rule. It's 1 times x to the 1 minus 1, which is 0. So you can also read like this, derivative of x with respect to x, the answer is 1. Or derivative of y with respect to y, the answer is 1. or in general derivative of a with respect to the same variable a, the answer is 1. So you don't have to do a typical power rule to show this, but you can understand that you have derived it using the power rule and your answer will be still 1. Now you can simplify this a little bit, cancel 2 and 6 3 times. So this is 3 times x to the 5, 3 times 4 is 12 x to the 3, and then you have a positive 1. In the next example, you have product of two functions and you want to find the derivative. So all you do is first multiply out this function, FOIL them, x times 2x, x times 3, negative 2 times 2x, negative 2 times 3. So let's write this. F of x equal to 2x square plus 3x when you multiply by x, and then negative 4x, negative 6. Simplify this, you get 2x square, negative x, negative 6. Now you want to do the derivative of this function, 2x square, negative x, negative 6. So you're good to distribute this derivative to each of the terms and then derive it. So it's derivative of 2x square, derivative of x, and then you have derivative of 6. So derivative of 2 times x square, 2 is a constant, 2 moves outside. Then you want to derive x square using the power rule. So you get 2 times x when you do the power rule for x square. Then you have derivative of x with respect to x. Your answer is 1. Again, this is power rule. Derivative of a constant, the answer is 0. Simplify, you have 4x minus 1. In the next example, you have a function of s, which is negative 12 divided by s to the 4. So you want to write the derivative this time with respect to the variable s. DDS of as. As is the function which you want to derive. So this is DDS of negative 12 s to the 4. S to the 4 can be moved to the top, rewritten as DDS of negative 12 s to the negative 4. Constant times the multiple, the constant always move outside. So it's negative 12 DDS of s to the negative 4. Let's do a power rule for s to the negative 4. So this is negative 12 times. The power rule says whatever is the exponent, this exponent goes to the front when you do the power rule. So I'm going to write negative 4. Then write the variable s. Then reduce the number by 1. So when you do negative 4, negative 1, this is the power rule. Simplify, this is 48 s to the negative 5. You can rewrite this as 48 s to the 5. In the next example, you have a product function square root times x plus 1. Distribute the square root to each of these functions. So it's square root x times x plus square root x. Now simplify this a little bit. Rewrite this function as x to the 1 half times x, x to the 1, and then times x to the 1 half. When you have exponents in the form of a fraction, it's easy to differentiate rather than the square root or a cube root. So simplify the first term. When you have the base is same, all you do is the base x is the same in the product, so you can add the power, you can sum the power. So this is 1 half plus 1, which is 3 half, plus x to the 1 half. Now that you have simplified the given function, you're good to differentiate the f of x, derivative of the function f of x. The function f of x, we rewrote it as x to the 3 half plus x to the 1 half after simplifying. Now you see that you have a sum of the function and you can distribute to each of these terms. So it's derivative of x to the 3 half plus derivative of x to the 1 half. Now derive the first function. You have 3 half, x to the 3 half minus 1 1 half. Then you have 1 half, derive x to the 1 half, which is 1 half minus 1, which is negative 1 half. So this is the final answer. In the next example, derive a rational expression. So you can divide each of these terms separate. You can separate x square divided by x square, negative 3x divided by x square, positive 1 divided by x square. Split the fraction. Now simplify. You have 1, negative 3 over x, and then plus 1 over x squared. Now you can rewrite this as 1, negative 3x to the negative 1, positive x to the negative 2. So whenever you have some x term in the denominator, you can move this to the numerator, change the exponents. That's easy to do a power rule when you have all the terms in the numerator. Now you want to rewrite the given function f of x. After simplifying, looks like this. 1 negative 3x to the negative 1 plus x to the negative 2. Now you're good to differentiate this function. So let's write differentiate d dx of f of x equal to d dx of the entire expression, which is 1 minus 3x to the negative 1 plus x to the negative 2. So this derivative here should be distributed to each of these terms. So we're going to write it as derivative of the first function 1 negative derivative of the second function 3x to the negative 1 positive derivative of x to the negative 2. Now let's use the formula which we learned in the starting of this section. Derivative of any constant is 0. Derivative of a constant multiple times x to the negative 1. The constant can be moved out, so it's negative 3. Then you do the power rule, so it's negative 1, x to the negative 1, negative 1. Derivative of x to the negative 2, it's negative 2, x to the negative 2, negative 1. Let's simplify this a little bit. So this is positive 3, negative 3 times negative 1, positive 3, x to the negative 2, negative 2, x to the negative 3. You can rewrite this as 3 over x square, negative 2 over x cube. In the next example, again you have a rational expression and you want to derive this given f of x. So if you want to differentiate or derive, all you do is split the fraction. So let's do that. You can rewrite this as x square divided by root x, 4x divided by root x, 3 divided by root x. And you understand that each of these root x can be written as x to the 1 half. So it's x square divided by x to the 1 half plus 4x divided by x to the 1 half and then 3 divided by x to the 1 half. You want to simplify this further, so let's do that. This is equal to x to the 2, you can take 1 half to the top, you're going to write it as negative 1 half. 4x to the 1, you can take 1 half to the top, it becomes negative 1 half. And then you have 3x to the, take 1 half to the top, it's x to the negative 1 half. Now simplify the exponents. So 2 minus 1 half will be 3 halves plus 4 times 1 minus 1 half is half and then 3x to the negative 1 half. Now that we have simplified to every extent possible, you're good to derive the function f of x. So you can write d dx of f of x. F of x, we rewrote it as the fraction simplified in the above step. So rewrite f of x as x to the 3 half, 4x to the 1 half, plus 3 times x to the negative 1 half. Now you're good to distribute this derivative to each of these terms, and then you have derivative of x to the 3 half, derivative of 4x to the 1 half, and then you have derivative of 3x to the negative half. So you have derivative of an exponential term here. The 3 half go to the front. The formula you do is the power rule. It's 3 half x to the 3 half minus 1. 3 half minus 1 is 1 half. Similarly, 4 is a constant, goes outside. Exponent goes outside. X to the 1 half minus 1 is negative 1 half. Then you have 3 is a constant, go outside. Negative half. So it's negative half, go outside. It's a product term. And then you have x to the negative 1 half, negative 1. Negative 1 half, negative 1 is negative 3 halves. So let's further simplify this. This is 3x to the 1 half. Simplify the fraction 4 and 2. So you have 2x to the negative 1 half. Multiply the product. 3 times negative 1 half is negative 3 half, x to the negative 3 half. So this is the simplified form of the answer. In the next example, for what values of x does the given graph of a horizontal tangent? Whenever you see this word horizontal tangent, you have to understand that the slope of the curve, if f of x is the given curve, the slope is always f prime, that should be equal to the 0. The slope of a horizontal tangent is 0. So given f of x in the problem, let's try to find the f prime, the derivative of the function. So let's do that. Let me write f prime below this and let me derive each of the function. Derivative of x cubed is 3x squared. Now I'm not going to write the d over dx symbol. You all are familiar with it. It's a derivative. So the same d over dx can also be written as f prime. So let me include one more step here. F prime is also d dx of f of x, which means I'm going to differentiate every term on the top, the third degree polynomial. So let me differentiate the first term x cubed, which is 3x squared. Then differentiate 3x squared, which is 6x. Differentiate x, 1. Differentiate 3, it's 0. So I'm differentiating each term on the top, and this is the new term I'm going to get on the bottom. I differentiate. So now you have f prime term, but the definition of horizontal tangent is f prime equal to 0. So f prime, which is the new term what we got as 3x squared plus 6x plus 1, can be equated to 0. The idea here is you want to solve for the variable x. So let's do that. Solve for the variable x. So first you want to try factoring directly, but that's not possible here. So you go by the quadratic formula. Do a quadratic formula for this. Suppose you have an equation ax squared plus bx plus c equal to 0. The solution of this equation will be x equal to negative b plus or minus square root b square minus 4ac divided by 2a. So you identify the term a, b, c, the coefficient, and plug into this formula. So when we do that for the 3x squared plus 6x plus 1 equation, we get x equal to negative b, which is negative 6, plus or minus b squared, that is 36, negative 4 times a, which is 3, and then times c, which is 1, divided by 2 times 3, which is 2 times 3, which is 6. Simplify this a little bit. You have negative 6 plus or minus 36 minus 12 is 24 divided by 6. So you have two roots, negative 6 plus root 24 divided by 6, and then negative 6 negative root 24 divided by 6. The quadratic equation here has two roots. So the question asks you for what value of x does the graph have horizontal tangent? So these are the two values of x for which the graph will have a horizontal tangent. In the next example, you're asked to find the first and the second derivative of this given function. So let's do that. Find f prime, which means you're deriving the function f of x. So let me write d dx of f of x equals, let me also plug in the f of x here. Let me going to write e to the x negative x to the 5. When you have sum or difference of the terms, you're good to distribute this derivative to each term. Derivative of the exponential is the same, so write e to the x. And derivative of x to the 5 is 5x to the 4 using the power rule. Let's do the derivative again, f double prime, which means you're deriving the function f prime. F prime is the function what you got in the previous step. So let me write f prime is e to the x negative 5x to the 4. So you're going to write this as d dx of, you can distribute this derivative to each term here. So let me write the derivative directly. Derivative of e to the x is e to the x. Derivative of 5x to the 4 is 20x to the 3 using the power rule. And this is your second derivative. So let me specifically say this is your first derivative. and this is your second derivative. The next one is a word problem. The equation of the motion of a particle is given by this particular equation, s equal to 2t cubed minus negative 5t squared plus 3t plus 4, where s is in the centimeter and t is in the seconds. So s is some unit which measures the distance and t is the time unit. Find the velocity and the acceleration as a function of time, and what is the acceleration after 2 seconds. So let's write. The distance s is given by 2t cube negative 5t square positive 3t positive 4. So let us derive this distance s. I'm going to derive the distance s with respect to the variable t. So I'm going to write d dt of s. So I'm going to do the power rule. I get 6t square negative 10t positive 3, and derivative of 4 is 0, so you don't have to write it. The derivative of the distance is nothing but the velocity. So I'm going to write this is the velocity function, and I can also represent this by v. So now let me derive this again. D square s by dt square. I'm deriving the derivative of s again. And deriving the derivative again is the acceleration definition. So this is the acceleration denoted by the variable a. So let me derive 60 square. I have 12t using the power rule. Derivative of 10t is 10. Derivative of 3 is 0. Now that we have found the velocity and the acceleration, in this last expression, let me plug in t equal to 2. Because you're asked what is the acceleration after 2 seconds. When you plug in t equal to 2, you have a at 2, because a here is a function of time. So I can write a as at. So a at 2 equal to 12 times 2. I'm plugging in t equal to 2, negative 10. Simplify, this is 24, negative 10. And this is 24, negative 10 is 14. Some important note about the derivatives. This is the first section where you are learning some formulas to do the derivative or the differentiation. So you have to be very, very careful when you derive the functions. This is not printed in your notes, so I'm going to write some extra problems as an explanation to understand the derivative. Suppose we are deriving a function, say x to the 6. You always want to compare this one using the power rule formula ddx of x to the n. All we can do is nx to the n minus 1. We do this if n is an integer. The n here, which is the exponent, is an integer. It can be 0, it can be plus minus 1, plus minus 2, plus minus 3, and so on, all the way up to infinity. Then you can do this definition of the power rule. And you call this as the power rule of differentiation, which you will see most often in many of the algebraic functions differentiation. So when we do this, I can differentiate x to the 6 as 6x to the 6 minus 1, which is 6x to the 5. This is what we did in the lecture section 3.1. Let me explain you a common mistake which sometimes the students do on the exam, and I don't want you to do this type of mistake. So let me pick one common mistake. Suppose you want to derive. Let me reverse the function. Rather than x to the 6, let me write 6 to the x. Sometimes students do this. They read this exponent. They read this as an exponent x, and they do a typical power rule like this. They move x to the front, they write like this x, and they write 6, and they reduce the exponent by 1, so they do x minus 1. if you observe carefully, this is not correct. The reason is you can do this only if the exponent is an integer, a number. But here the exponent is x variable, so you cannot bring x to the front and reduce x by 1. So this is not correct. This is wrong. We can do this only if the exponent is a number. So let me do one more example. This is correct. X to the, this is 2020. We cannot forget this year. So let me write 2020. Let me derive x to the 2020. So the power rule of differentiation says that you can take this number on the top to the front when you differentiate. So I'm going to write this as 2020, then you have x, then you reduce the power by 1. So 2020 is reduced by 1, which means 2019, the previous year, 2019. So again, this is a power rule of differentiation, which you will see several times in calculus 1, and your calculus 2 is also dependent on your calculus 1, and you will see this power rule many times in your calculus course. So make sure you all understand how and when to apply the power rule of differentiation. You can do this only if the exponent is an integer. You cannot do this if the exponent is a variable x. And later in one of the sections in chapter 3, you will learn how to differentiate a to the x, which will have a natural log function, and you can do this. Again, this is not a power rule. Please don't do a power rule formula for this. This is not a power rule problem. It's not a power rule because this exponent x is not a constant. So you want to make a note of this. And this is one common mistake which most often I see in some of the quizzes or exam. Again, I really don't want your class to repeat this mistake. So make sure you all understand how and when to apply the power rule of differentiation. We'll end this lecture here.